Okay, we are on chapter 2, section 4, talking about radioactivity and radioisotopes. So, whenever you have an atom that spontaneously gives off energy, we call that nuclear radiation. And this occurs in unstable atoms. And any atom that gives off that energy spontaneously, we call it radioactive. So if it spontaneously gives off energy, it is radioactive. And we see radioactive elements in nature, and we can also make them in the lab. So you can change an atom in terms of number of neutrons to get different isotopes. And so some isotopes are radioactive and some isotopes are not. And the first natural source of radiation was found in 1896. And it was a collaboration between Henry Becquerel and Marie Curie and her husband, oh my gosh, what was his first name? But it was the Curies. And they have a photographic plate, and this is what they used to develop. It wasn't film back then, it was a plate. And so what happened was they placed this plate next to uranium, and in the dark, which is not, it's not supposed to do anything until you turn on the light and then you expose it, and then you'll expose the plate or the film. In the dark, they exposed the plate to the uranium and they got a picture. And so they figured out that something is being given off by this radioactive substance. So most isotopes, right? We talked about isotopes before. We just know that they have a different number of neutrons. Most of them have a very stable nucleus and they're not radioactive. But some are radioactive, and by giving off radiation, they become more stable. And so we call this process radioactive decay. So as they undergo radioactive decay, they become more stable. So any isotope that emits radiation is called a radioisotope. So you can get radioisotopes from the earth, or you can make them in a lab. Most of them we get in the lab. So all of the isotopes of elements with an atomic number of 83 and higher are radioactive. But there are some exceptions. Some lower elements have radioisotopes, for example, gallium. Gallium, here's two examples of isotopes of gallium, gallium-69 and gallium-67. Gallium-69 right here is stable. But if you take away two of those neutrons, right, we're leaving the protons the same, but if you take away two of those neutrons, now our mass number goes down to 67, now it is radioactive. And this is one of those isotopes radioisotopes that's used in diagnosing some different cancers and things. So there are 5 different kinds of forms of radiation that you need to know. And they are alpha radiation, beta radiation, gamma radiation, and then positron and neutron. And so we're going to talk about each one and what they're made of, and we'll come back to this kind of summary slide again. So an alpha particle is represented by the Greek letter A, or alpha, and it's actually a helium nucleus. So remember, a helium nucleus has 2 protons and 2 neutrons. So the bottom number is telling us our number of protons, and the top number is telling us our neutrons and our protons. But it's an alpha particle. It does not contain any electrons. So because there are no electrons, we have a positive 2 here and no negative charges. So it ends up with an overall positive 2 charge. So alpha particle has a positive 2 charge. Next one's beta. And in beta radiation, there's a neutron. And that neutron will eject what's called a beta particle. The beta particle is actually a high energy electron. And because it's an electron, it carries a charge of -1. So then that neutron that ejected that electron becomes a proton as a result. And so we show that here because this is our number of protons, right? And so we had that neutron that became a proton. And it also released an electron. So because it's an electron, so I use the letter E, we know that it's releasing that high energy electron, and so it has a charge of -1. Gamma rays. Gamma rays are high energy radiation, but they don't contain any particles, so they have no mass. And gamma rays are released when an unstable nucleus gets rearranged, and now it's in a more stable state. And so you're not actually releasing any particles, you're actually releasing rays. That's why they call them gamma rays. Very, very high energy. And X-rays are similar to gamma rays, except they're not as powerful, they're not as strong, right? And so the way we show this is this has no mass, and so you have no protons, no neutrons, so we put a 0 and a 0, and we put that Greek letter gamma. A positron. A positron, ooh, I'm going the wrong way. Okay. A positron has the same mass as a beta particle, but it's positively charged. So at least I named this one right. A positron has a positive charge. So it is represented as a 1 down here, right? And the E. And so it has the same mass as a beta particle. And we know a beta particle is the emission of a high energy electron, right? So it has the same mass as that high energy electron, but it's the opposite charge. So the decay chart changes a proton into a neutron. So you have a proton going into a neutron, and it will emit that positron. So this is kind of like a positron's kind of the opposite of an electron. And so that positron then collides with an electron, and that collision releases gamma rays. And so this is what they use in PET scans to look for cancer. This is the radioactive isotope that they use. Okay. All right, a neutron. A neutron has no charge, right? We know that. We abbreviate in 0, right? It has, and it's represented this way, right? Because this is supposed to be protons, P+, and then this is protons and neutrons. And so we know that we have only one neutron. And so what we use neutrons for is we can actually use them to convert an element from one isotope to another isotope. And so we go from something relatively stable to something unstable to cause radioactive decay. So I'm going to show you an example here. So, and whenever we write equations like this, it's kind of like we're balancing an equation, right? And so we start out with this element right here. So this is boron 10, right? And there are two different ways to write that. You could write the name with the mass number, or you could write the element where the mass number's on top and the number of protons on the bottom. So if we bombard this atom with a neutron, what's going to happen is we now have to add our mass numbers together of the neutron and of the boron. And so when we do that, we get 11. So this has 11 neutrons, but the number of protons didn't change. So we had 5 here, 5 plus 0 is still 5. So we still have boron. So we start out with a stable isotope. We added a neutron, and we got something unstable that will undergo radioactive decay. So we can use this to cause radioactive decay. So here's our kind of our summary, right? We have an alpha particle. We can abbreviate it as a little symbol alpha. And we know that it has 2 protons and 2 neutrons. So it carries a charge of +2 because it's a helium atom or a helium nucleus, and it has no electrons. So that charge comes from the 2 protons. We have the beta particle. The beta particle is where a neutron emits that high energy electron, and then the neutron gets converted to a proton. So we have to remember that we have 1 proton in there. Then we have gamma particles, which have no mass. They are just high energy rays. So we have zeros for our atomic number and zeros for our mass number. And then we have positron. Positron is where a proton goes to a neutron and it emits a positron. And we said a positron is kind of like the opposite of an electron. And then neutrons we can use to add to an atom to induce radioactive decay. Okay, so what does this matter for the body, for patients, right? So radioactive emissions, all of these things, radioactive emissions, contain lots of energy, and they will interact with any atom they come into contact with. And the interaction that they do is they ionize atoms. So when we say they ionize atoms, they actually remove electrons from the atoms of any substance they interact with. And this is super dangerous. It makes the atoms unstable, it makes them reactive, and it can affect, in a human, it can affect a cell's chemistry, it can affect a cell's DNA, its genetic material, and it can cause cancer. And so the more you get, the more likely you are to get cancer. And so depending on the type of radiation it is, the higher the energy it is, the more it can penetrate into the tissues of our bodies. And so if you work with radioactive materials, which I actually did in the lab, you're going to wear a lab coat, you're going to wear safety glasses, you're going to wear goggles. And what I did was I actually sat inside of a hood. So there was a big glass that came down in front of me. And then I had my radioactive substance and it was inside of a protective container. And before I opened it, there was an additional shield inside of the hood that I then went and put the container behind that shield. So I had a shield, I had a glass, well, it was really plexiglass partition, and then I had all my protective gear on, and I wouldn't open the lid until I had those 2 layers of protection plus whatever I was wearing to prevent radiation. And so you actually wear a badge, and I wore a badge on my lab coat. Some people, it's like a ring on their finger, but I wore mine on my lab coat, and it's linked to your social security number. And so it counts the amount of radiation that your body is receiving. And if you get too much radiation, you become banned from working with radiation forever because it can lead to cancer. So we really want to monitor that. So someone who is an X-ray technician would have a badge. Anybody who works with radiation on a semi-regular basis would have one. So if you look at the different ones and look at what's dangerous, I worked with beta radiation. So you did want to have some protection, right? Alpha is the least dangerous as long as it's on the outside of your body. Your skin will protect you from alpha radiation, and you've got skin just about everywhere, so you're pretty well protected. But if it becomes aerosolized and you inhale it, or it's on something and you ingest it, that alpha radiation is very dangerous and can destroy your internal organs. As long as you have skin between you and alpha radiation, you're okay. But once it gets inside, it's dangerous. So beta is a little more dangerous. You need to have some protection there. And I had 2 layers of protection. Gamma radiation is a little bit stronger. X-ray is not as strong as gamma, but close. And then neutrons penetrate the most. And so this just kind of gives you an idea of how far the different types of radiation go and what's going to protect you. So like the beta radiation, when we stored it inside of aluminum boxes. And so it would protect everything around that radiation source from getting any kind of radiation. I didn't work with anything more dangerous than that. I was happy not to. So how do we measure radiation, and how do we know it's too much? So we look at the Sievert, which is the SI unit to measure the effect of biological damage. So how much radiation is going to cause a problem? Well, we all get some radiation. It doesn't matter. We're all exposed to ionizing radiation due to cosmic rays from all the different, you know, stars out there. Um, there are naturally occurring radioactive elements inside the environment around us. And so you're going to get some, but not a whole lot. We also measure radiation in millirims or rims. And so millirims or rims tell us how much radiation you're getting per kilogram, not biological damage. The biological damage is the sievert. The millirim is the amount of radiation you're getting. And if you look over time, our exposure to radiation has actually increased a lot, 40% since 1980. It's still not dangerous, but it has gone up. And this is because we use these radiation sources in all kinds of different medical procedures, really strictly from that. So, but what happens when you get too much? Because you can. So it's dependent upon how long you're exposed to the source and how much you are exposed to. So if you are exposed to radiation over a long period of time and it's very low level, it's fine, not a big deal. But if you have a short-term, very high, intense dose of radiation, you're going to cause very, very rapid cellular and tissue damage, and you won't be able to recover. So there are some cell types that are more susceptible to radiation, and those cell types that are rapidly dividing are more susceptible to radiation. So this is why we use radiation to kill cancer, because cancer cells grow at a much more rapid rate than normal cells, because they're not really doing their job. All they're doing is eating and growing, eating and growing, eating and growing. They don't do any functions. It's like weeds in the garden, right? Weeds grow faster than your plants, but they're not producing a fruit. They're not doing a job. They're just kind of taking over. And that's what happens with cancer cells. So, but here's the problem. When we treat somebody who has cancer with radiation, you have off-target effects. And your immune cells, your white blood cells, are very rapidly dividing. And so you become immunocompromised if you're having cancer treatments. Hair cells are rapidly growing cells. And so if you have radiation, you can lose your hair. Another common symptom of radiation and chemotherapy treatments, both things target rapidly dividing cells, are the stomach lining cells. So the ones that produce the mucus that protect your stomach from the acidity. Well, if you lose those stomach lining cells from the radiation, then you're going to be nauseous and you're going to be sick. And so that's another symptom of cancer treatments. So if you look at exposure in millirims, you can see everybody's going to get some kind of low level exposure, and we can't see a clinical effect of that. But once we start increasing, the first thing that we see affected are our white blood cells, our immune cells. Then you move on to a higher dose and you see even more decrease in white blood cells, and there's your nausea and vomiting, right? Because of those stomach lining cells. Even more, now we're at the point where we call this radiation poisoning. So this starts to get really serious. You see an appetite loss, you see nausea, diarrhea, hair loss, spontaneous abortion. And it takes a while, but the body can recover from this. Go up one more, moderate radiation poisoning. This takes a long time to recover, and you are going to have some form of permanent damage. And then you go up even higher, and we call this the lethal dose. So this is the lethal dose for half the population after 30 days. And so that would be very, very, very terrible. So how do we write a nuclear equation when we talk about radiation? We're going to start with some reactant. And so this, for example, is uranium. And uranium is going to decay into a new element. Here's thorium. Oh, this is the next section. Okay, so I want to stop here. I'm stopping here, and I'm going to our in-class problems. All right, so we're going to do some of our in-class problems before I get too far ahead of myself. All right, so let's talk about our isotopes. Oh no, here. Okay, radioactivity. Get on the right track. I put you this chart back here so that you would have something to reference. So if you need to go back to it, that way you wouldn't have to keep flipping back and forth. Okay, so if the symbol for an alpha particle is He, 4 on the top, 2 on the bottom, explain how an alpha particle differs from a helium atom, right? If I told you to write the symbol for helium, you would write He, and you would say, okay, that's 2 protons, and I know I have 2 neutrons, so how is this different? Well, this is the atom, right? But the alpha particle has no electrons. So even though we didn't write this with electrons, this atom with electrons, it really does have it. It's assumed so. But when we say alpha particle, we write the same symbol, but this one is neutral, whereas the alpha particle, that's this, has a charge of +2. Okay. What form of ionizing radiation has the greatest penetrating power? So you would go back and we would come over here and we'd say, oh, wait a minute. Okay, I want to go back. Okay, and which one has the strongest penetrating power, right? You could say neutrons, and you could really say gamma and X-rays, because neutrons is causing the decay, but gamma is actually the radiation. So we're going to say gamma rays, right? And why am I not writing? Neutrons. Okay. So 2.4, no, that's for class. 2.5. All right, how much radiation is the average person exposed to annually from all sources? So this one you actually have to go in and you have to do some calculations. So if you go back to your book, what you're going to see is that you have about, and you have 2 different units that you can put on here, 0.0062, this is just from your notes, right? And so, or you could call this millirems, because remember, this is telling you if you have clinical damage, right? Cellular damage, or you could talk about millirems. And this is telling you how much amount of radiation per kilogram of body tissue. So either unit would be fine, right? Okay. A routine dental exam often includes x-rays. I mean, we do this all the time. And it exposes a patient to a total of 5 millirems of radiation. Would this cause radiation sickness in the patient? And if so, what would be the effect? Well, in order to the max, so the max without clinical effect is equal to 20,000 millirems. And that really should be a lowercase r, millirems, right? So if you're getting only 5 millirems, you're not going to get sick. How many x-rays would it take before you would have something? So you could say 5 millirems. How many x-rays? So we know for one x-ray, it's 5 millirems. So how many of those would I have to do to get to 20,000 millirems? So if you do divide by 5, right? X, so 20,000 divided by 5, you would have to get 4,000 sets of x-rays before you would actually have clinical damage. So you should get your x-rays, right? All right. Okay. So use this table and tell what type of ionizing radiation is produced in the nuclear equation shown. So we're looking at our nuclear equation, which I don't want to do yet because I haven't showed you nuclear equations. So I'll show you that next time. All right, that ends this lesson.